Hi class, welcome again to another session on digital principles and system design. So in the last video, we discussed an introduction about FPGA and then we went on to see the various types of systems that Xilinx has provided to us. The most commonly used or the most popular of the systems that was provided by Xilinx is the Spartan architecture. Now let us have a look at the block diagram, and if possible we'll have a detailed discussion about the entire block diagram in this video. The generic block diagram of a Spartan system is presented here. You can see there are various IOBs, which is the input output buffers. You have CLBs, 4 CLBs here, which are the configurable logic block, and then you have various switch matrices which control the flow of the signal by switching the lines. Then you have the horizontal and the vertical lines which carry instructions. So let us have a detailed look at each block now. Starting off with the configurable logic block, there are more than one CLBs in an FPGA system, and each has a programmable lookup table, and then it also has multiplexers, registers and paths for control signals. There are two function generators, F and G for the lookup tables, and these generate any arbitrary functions of 4 input, while the third function generator, H, generates a Boolean function with 3 inputs. Now when I say a function generator, it's not the generic function generator that you'd use in the laboratory to do your experiments on frequency response plotting of an inverting amplifier or something. These are function generators because they generate a Boolean function, right? So H block receives input from F and G lookup tables or from an external input, depending on how you have configured your FPGA chip. Now, combining these 3 function generators, you can have the following options. First, you can have 3 different functions of 3 independent set of variables. Then you have an arbitrary function with 5 variables, an arbitrary function of 4 variables together with another function of 6 variables, and some functions of 9 variables. So these are the various types of function generations that is possible using your CLB. Now there are 2 storage devices per CLB, and that can be configured as an edge-triggered flip-flop with common clock. In the 4000 series of your Xilinx family, the storage elements can be configured as flip-flops or as transparent latches with common clock and an enable. So these storage elements can receive inputs either from function generator or from the input pin, or DIN pin as it is called. The other elements can receive an external input from the function generator. Now the function generators can, external input from outside. The function generators can also derive 2 outputs directly and independent of each outputs of the storage elements, right? So these storage elements are often connected to interconnected network, and they are driven by a global set reset during power up. So this global set reset is programmed to match the programming of the local set reset for each storage element to maintain synchronization. Then you have the distributed RAM in your FPGA, in your Spartan system. So the 3 function generators within the CLB can be used as a 16x2 dual port RAM or a 32x1 single port RAM. However, in XE4000 devices, block RAM is not available, and the CLB can form an array of memory elements. In Spartan devices, both block RAM as well as distributed RAM are available. So let us have this is how the distributed RAM structure of a Spartan system looks like. So you have the input register, you have the write row select, so you can select which row you want to write at. Then you have the read row select, you can also select which row from the memory that you want to read the device from. You have the write control and the read out. Write control would actually give you the access to write into the memory, and read out would allow you to read from the memory. So these are various control signals that would help you in operating the that will help you to perform certain operations in the memory. Is the simplest way to describe it. So when you write into the memory, you need the write control, and when you read from the memory, you need the read out. However, in the same instance, you can't do both writing and reading simultaneously. So if you are writing in the memory, you should be writing first and then reading it out, and so on. So interconnected resources are these are grids of switch matrices which overlay on the architecture of CLB to provide general purpose interconnection or branching or routing through the device. So these switches decide which line goes where, because it's a very complicated system. You've got so many parts that you need something to actually control the flow of the signal. Now there are three types of interconnects: the single length lines, the double length lines, and the long lines. So a grid of horizontal and vertical single length line connect and the array of switch boxes which result in reduced number of connections between the signal path with each box. So basically short lines which are which would lead into it would lead into a more neater connections. So it is less confusing to follow the path of the signal. So there is also a tri-state buffer in each CLB, and that derives signal to the nearest horizontal line above or below the CLB. So this tri-state buffer also contributes to controlling the flow of signal. So this is a general block diagram. So you have the switch matrices, and each of these small short lines, they are the single lines, and then the switch matrix actually decides which signal goes to which line. Basically it controls the flow of signal. You also have the double length and long wires. So these lines here which are crossing over, they are the double length lines, and the single long straight line is the long length wires. So you have vertical long wires as well as horizontal long wires, depending on how your how your chip is developed. So you can have all these. So direct interconnect lines provide routing between adjacent vertical and horizontal CLBs in the same column or same row. So if you have CLB here and CLB here, so direct connection between the two, because these are two adjacent points. So direct connection between the two can be given by direct interconnect lines. There are relatively high speed local connections through metals, but they are not as fast as hardwired metal connection because the delay incurred is it does incur some delay. Then you have direct interconnect lines that do not use the switch matrices. Thus they eliminate the delay because of the switch matrix. However, it is still slower than hardwired metal connection. Now double length lines traverse the distance of 2 CLB before entering a switch matrix, thereby skipping every other CLB. So it's just connection between alternating CLBs. So these lines provide a more efficient implementation of intermediate length connection, and they eliminate the switching path as well. Therefore they reduce the delay in the path. So how fast you want your signal to transmit from one point to the other, you can choose any of these interconnections.